We've been talking about space for a little while now. One of the things that we haven't broached is just quite how big space really is. Whenever we're talking about distances in space, we often need to use different units and different ways of measuring distance because meters are just not good enough. And what we're going to talk about today are some of those different ways we have of measuring distance. I'm also going to do a quick recap on the Doppler effect at the end of this as well, just because it's quite quick and it fits in nicely here. So our first unit that we're going to talk about is the light year. Hopefully you already know that a light year is the distance travelled by light in 1 year. Often when students try and define this in exams, one of the common mistakes they make is they talk about it being an amount of time. You know, because it's a year, you automatically want to think time. But remember, it is the distance that is travelled by light in 1 year. And since light travels 300 million metres per second, that's 300,000 kilometres per second, that's 18 million kilometres per minute, 1.08 billion kilometres per hour, which is 26 billion kilometres per day, that is 9.5 trillion kilometres per year, or 9.5 times 10 to the 15 metres. You see now why we don't like metres, they're a bit useless. So that's 1 light year. So that's our first unit. Second one is a little bit smaller. It's the AU, or the astronomical unit, and this is defined as the mean radius of the Earth's orbit around the Sun. So it's the average distance the Earth is from the Sun, because obviously you know that we have an elliptical orbit, so there are times when we're closer and further away. The AU is just the average of that, and that works out at 1.5 times 10 to the 11 metres. So it is in fact smaller than the light year. Unsurprisingly, because we should know it takes about 8 minutes for light to reach us from the Sun. So you can see the difference in magnitude there. Next up we've got the parsec, and 1 parsec is defined as the distance to a star which subtends an angle of 1 arc second to the line from the centre of the Earth to the centre of the Sun. I'm going to show you a picture that will make that a lot clearer. If you're ever asked to define the parsec, I would probably suggest if you can write that out, that's great, but you may also want to draw the diagram as well. They quite often actually just ask for the diagram, so it's very useful to make sure that you know that. But that works out as being 3.1 times 10 to the 16 metres. So that is bigger than the AU, but also bigger than the light year as well. Arc second, just in case we weren't sure, 1 arc second is 1 degree divided by 3,600. We can also do that in radians if you want, so 360 degrees is 2 pi radians, so 1 arc second is 2 pi divided by 360 times 3,600, which gives you 4.85 times 10 to the minus 6 radians. So, I'm just going to show you what I mean by the parsec. And in order to do that, I need to talk about something called stellar parallax. So, stellar parallax is where nearby stars appear to shift against the background of more distant ones due to the motion of the Earth about the Sun. Just to illustrate this, as long as there's no one looking and you don't feel silly, what I suggest you do is focus on something that's relatively far away from you, close one eye and stick your thumb so it is just covering up the thing you're focusing on. So maybe on the door handle of the door or something like that. So you close, say your left eye, line your thumb up so it completely covers the object you were looking at, then switch which eye is open. And what you'll find is that it looks as though the background has shifted against where your thumb was. That's the same effect that we see with space. So to show you what it sort of looks like, if we're looking at, we're on the Earth and it's June, and we're looking at this nearby star here, this is our field of vision against these distant stars. This is what it might look like. So this star would look like it was just above this red one in June. 6 months later, we are now looking from the other side of the Sun. This is the line that we're looking on, and it looks like this nearby star is now shifted. It was here, it's now here. So it's now, it looks like it's moved, and that is stellar parallax. And what we can do is measure this angle here by taking these measurements of where this star appears to be in the sky. And this angle here is the one that we then use to calculate how far away it appears to have moved. So if we go back to thinking about it as being a parsec, what we do is we use basically a bit of trig. So we would measure this angle here, the whole one as being 2 theta, and then we'd half it because that will give us this angle here. We measure 2 theta because it's easier, it's bigger, and it means that we've got something more accurate to do with. So the distance that we're interested in from us to the star is d here. The angle that it subtends is this angle here, and this distance here is 1AU. And then all we do is just use a little bit of trig. So tan theta is going to equal r over d. So that gives me that the distance that the star is from us equals the radius, the 1AU, divided by tan theta. Now, just because theta is going to be very, very small, tan theta is basically going to equal theta if we do it in radians. So that boils down to saying that d equals r over theta. So for the definition of 1 parsec, theta would be 1 arc second and r would be 1AU. So if you were to draw the diagram to define a parsec, I'd expect to see this, so star, sun, Earth rotating around the sun. Label this distance as 1AU, label this distance as d, and then this as your angle of 1 arc second. And that is the explanation of what 1 parsec is, and you obviously want to say your d is 1 parsec. Okay, so often we want to be able to calculate exactly how far away we are in parsecs, and we just want to be able to go there straight there from the angle in arc seconds. And the easy way to do it is the distance away in parsecs is just 1 over the parallax angle in arc seconds. So for instance, just to give you some examples here, if the parallax angle is 1 arc second, the distance away in parsecs is 1. But that should be easy because that's just the definition. If it was half an arc second away, we do 1 over a half, which gives us 2 parsecs. If it was 0.1, we do 1 over, it gives us 10. 0.01, it gives us about 100. Just as a note, we're kind of limited with this because the angles are very, very small, so there's a limit to how accurately we can measure them. So a distance of about 100 parsecs for a ground-based telescope is the best that we're going to be able to do. Okay, so those are our 3 units. So we've got the AU, the light year, and the parsec. We need to be able to use them, and we need to be able to convert between them, which is really straightforward. They won't expect you to memorise the numbers. You need to know the relative sizes of them, but you don't need to remember exactly how many meters each is. So I did say I'll very quickly talk about the Doppler effect, because it's going to come up when we talk about cosmology later. So the Doppler effect, I hope you're all aware, is the idea that when something emits a sound wave and then moves, the sound wave gets compressed, or appears to get compressed at the front and stretched out at the back. And it makes that ambulance sound, like you can hear when it's going past you. It sort of changes the pitch as it goes forwards and backwards. Just play it here. So you can hear that the pitch appears to change, and that's because basically as the ambulance is going forwards, the sound wave gets compressed, which decreases the wavelength, which increases the frequency. And behind, you can see that the wavelength gets increased, which decreases the frequency, so it changes the sound. Now, obviously, this can happen with light waves as well as sound waves, and radio waves as well, for that matter. So, with light waves, in front of the moving object, we get decreased wavelength, increasing frequency, makes it appear bluer. So it would shift it towards the blue end of the spectrum. If you're behind the moving object, if the object is moving away from you, we get an increase in wavelength, decrease in frequency, which makes the light appear redder. So we get exactly the same thing as we did with our ambulance, only this time it's the source that's emitting the light that's moving. If you're in front of it, if the object was moving towards you, it makes the light given off appear bluer. If you're behind it, it makes the light given off appear redder. So that is the basics of the Doppler effect. But we now need to be able to use the equation for this, and there is an equation. It's called the Doppler effect equation. There is a limit to when you can use this. You can only use this equation if the speed of the object is considerably less than the speed of light, because otherwise we get into all sorts of relativistic issues, so we're not going to worry about those. As long as your radial speed is much less than the speed of light, you can use this. And the equation is just this. It says that the change of frequency over the source frequency is equal to the speed that the object is moving divided by the speed of light. Really simple. However, we can also use this for wavelength, because it's equally true for wavelength, has the same relationship. The change in wavelength over the source wavelength is equal to the speed over the speed of light. So I can do it for lambda, is equal to v over c. Now in each case, the Doppler shift, which we give the symbol z, is equal to that ratio. So it's equal to the change in frequency over the original frequency, which is equal to the change in wavelength over the original wavelength, which is equal to the radial speed over the speed of light. And that ratio is just called the Doppler shift. So that can just be a little shortcut. But remember, you can only use this when v is much smaller than c. Okay? So what this looks like when we have spectra is a little bit like this. So here I've got continuous spectrum, and I'm going to make it go through something so that I can see an absorption spectra. So if my source of light is stationary, I would expect the alpha hydrogen lines to be in these positions here. This is exactly where I would expect it to be. Now, if the source of light is receding, we would see those lines shift. Now note that the spacing stays the same, but the position has just shifted towards the red end of the spectrum. And if it was approaching us, we would see it shift towards the blue end. So some of them have shifted right out of the visible, and I can only see those three. But from their spacing, I can still tell what it is that's giving it off. So that is Doppler effect, and linking it back to the spectra that we did last session. We're going to talk about how the Doppler effect has been used to look at the history of the entire universe. We're going to go right from the beginning to possible endings as well. And that's what we're going to talk about next time. Remember, got any questions? Just ask when you see me.